Section: Introduction. We're going to talk about how large language models, LLMs, have changed the game in many applications, particularly in how machines interact with human language. The key to this transformation is training these models on a massive scale. To do this in a reasonable amount of time, we need to spread the computations across multiple devices. But there's a catch. The standard way of doing this involves using devices that are located close to each other and have fast connections. We'd love to be able to use a wider range of computational resources, even if they're far apart, to build even more powerful models. But there's a big obstacle in our way: communication latency. When devices are busy calculating gradients before sending them back to a central server, the time it takes to communicate can become longer than the time it takes to compute, creating a bottleneck in efficiency. Local stochastic gradient descent, Local-SGD, is a group of optimization methods that can help reduce these communication bottlenecks. These methods involve each device performing multiple local gradient steps before syncing their parameter updates with a parameter server. While Local-SGD can improve training efficiency by reducing communication frequency, it can suffer from the straggler effect caused by devices of different speeds. For example, faster devices are left waiting for slower ones to catch up, which undermines the overall efficiency of the system. Moreover, all devices are forced to communicate at the same time, requiring a high bandwidth connection with the parameter server. Asynchronous Local-SGD presents a more viable solution, as it allows the server to update the model as soon as the updates of a worker are available, thereby enhancing computational utilization and minimizing communication bandwidth requirements. In this study, we're going to explore the feasibility of asynchronously training LLMs using Local-SGD. We'll build on previous works that have tried to alternate steps on subsets of workers or randomly drop certain subset of workers during synchronous Local-SGD. We'll introduce our high-level design for the asynchronous training framework, discussing how each worker determines which data shard to train on, for how many steps, with what learning rates, and how the server updates models asynchronously. We'll also conduct an empirical study of various existing optimization strategies suitable for asynchronous Local-SGD. This includes both worker-side optimization, inner optimization, and server-side optimization, outer optimization. We'll uncover a key challenge in utilizing momentum effectively. We'll introduce two simple and effective techniques: the delayed Nesterov momentum update, DN, and dynamic local updates, DYLU. These techniques, when combined and evaluated on training language model, allow asynchronous Local-SGD to approach synchronous Local-SGD in terms of perplexity versus the total number of local updates, and further improve asynchronous Local-SGD versus synchronous Local-SGD in terms of perplexity versus wall clock. In this study, we'll focus on the distributed optimization of shared model parameters across multiple data shards, with multiple workers. The primary goal is to minimize the sum of the losses for each data shard, where the loss is the cross-entropy loss for next token prediction in language modeling. We'll extend the definition of Local-SGD in this work to include not just the original Local-SGD method, but also its variants that incorporate advanced optimization techniques. We'll particularly focus on DLOCO, which sets the standard for synchronous Local-SGD in language modeling. Each worker performs multiple local updates using an inner optimizer on their data shard before sending the parameter change back to the server. The server then computes the aggregated outer gradient and applies an outer optimizer to update the model parameters. A key insight from DLOCO is the optimal use of Atom W and Nesterov momentum as the best inner and outer optimizers, respectively. Section Summary. Large language models, LLMs, have revolutionized natural language processing, but training them at massive scale requires distributed computations. However, communication latency between devices can hinder efficiency. Local stochastic gradient descent, Local-SGD, reduces communication bottlenecks by allowing devices to perform multiple local gradient steps before syncing with a parameter server. Asynchronous Local-SGD further improves efficiency by updating the model as soon as worker updates are available, minimizing communication bandwidth requirements. This study explores the viability of asynchronously training LLMs using Local-SGD and proposes techniques to approach the performance of synchronous training. Section: Async. Local-SGD Framework. In this section, we'll explain the design of an asynchronous Local-SGD pipeline. We'll assume that a central server is in control of all workers and is responsible for gathering their updates asynchronously. First, let's talk about how we sample data shards. Unlike in federated learning where each device has its own data, in distributed optimization, the user can decide which data shard is assigned to which worker. This can even be done dynamically. To ensure that learning progresses evenly across different data shards, since workers can vary, we select a data shard for a new local optimization round based on its learning progress. This means that we choose a shard that has fewer learned data points compared to its total data points. The more a shard is undersampled, the higher its chance of being selected for training. This way, we make sure that shards with slower progress get more attention, balancing the learning progress across all shards. Next, we'll discuss how we schedule learning rates. Asynchronous training can lead to uneven progress across different data shards, especially when workers are allowed to take different numbers of training steps. To address this, we assign each data shard its own learning rate schedule. We use a linear warm-up combined with a cosine learning rate decay. The total number of training iterations for each data shard is represented by T. The learning rate changes depending on whether the current iteration number is less than or greater than the warm-up period. If the final iteration count for each data shard varies due to the unpredictable nature of asynchronous training, we set the minimum learning rate to a small positive value. This ensures continued progress even if the number of iterations exceeds T. We also adjust the difference between T and the warm-up period to be non-negative and ensure that the ratio of the difference between the current iteration number and the warm-up period to the difference between T and the warm-up period stays within the range of 0 to 1. This helps maintain effective learning rate adjustments throughout the training process. In asynchronous training, the completion time of each worker's tasks can vary. If one worker finishes training shortly after another, it might be beneficial for the first worker to wait briefly until the server processes updates from both workers before receiving the updated model for its next training task. However, this waiting period should be minimal and occur only when necessary. If no other worker completes its task within the grace period while the first worker is synchronizing with the server's model, the first worker should promptly commence its new training task using the server's current model. Finally, we'll discuss asynchronous task scheduling. We use tau to denote the actual wall clock time and T to denote model updates. We start the first training job for all workers with the initial model parameter. The training function implements the data sampling technique and performs the learning rate scheduling mentioned before. We reset the starting time of the grace period to infinity because we want to synchronize with a worker only when its completion time is within the grace period. The main asynchronous Local-SGD training loop attempts to get a completed worker. We retrieve the earliest completed worker that we have not yet processed yet, as long as its completion time is still within the grace period. If no such workers exist, the function will return null. When such a worker is found, we synchronize its update with the server model. When no such workers are found, we assign new training jobs for all completed workers and empty the list of completed workers. For the sake of reproducibility of research, we implement a deterministic version of the algorithm with fake training time based on real-world device statistics. We validate the correctness of the training pipeline by simulating synchronous updates using the asynchronous framework. Section Summary. The section describes the asynchronous Local-SGD pipeline design, where a central server controls workers and asynchronously aggregates their updates. It also explains the data shard sampling technique to balance learning progress across workers and the learning rate scheduling approach for each data shard. Additionally, it introduces the concept of a grace period for model synchronization and presents the asynchronous task scheduling pipeline. Section: Optimization Challenge. Let's delve into the challenge of optimization and its impact on language modeling performance in asynchronous Local-SGD. We'll start by experimenting with different combinations of inner and outer optimizers. Here, we'll use the notation A plus B to indicate A as the inner optimizer and B as the outer optimizer. We'll test combinations like SGD plus Nesterov, SGD plus Atom, Atom W plus SGD, Atom W plus SGD momentum, Atom W plus Atom, and Atom W plus Nesterov. We'll adjust the hyperparameters for each combination separately, but for Atom W as the inner optimizer, we'll stick with the default values. We'll assume we have 4 workers, and we'll show their device speed in a figure. We'll then apply asynchronous Local-SGD fine-tuning to a language model with 20 million parameters, running 64,000 steps per worker, which totals to 256,000 local steps. The initial model checkpoint was pre-trained for 24,000 steps with Atom without distributed training. We're choosing to fine-tune with Local-SGD because it's been observed to work well in fine-tuning, although it's less efficient from scratch. However, others have also observed that Local-SGD works well even for training from scratch. We'll follow the learning rate scheduling and task scheduling procedures described in a previous section. We'll use 50 inner steps across all workers in all experiments by default. The result will be shown in a figure. Our analysis reveals that the best results come from combining Atom W as the inner optimizer with Nesterov momentum as the outer optimizer. This aligns with findings from synchronous training methods like the Local method. Interestingly, using Atom W as the outer optimizer is less effective. This could be because Atom W, which is derived from Atom, introduces a normalization effect. This can be counterproductive in Local-SGD where pseudo-gradients tend to be larger than true gradients, potentially slowing convergence. When Atom W is used in the inner optimization, SGD, SGD momentum, and Nesterov show comparable performance. However, Nesterov not only stabilizes the learning curve but also slightly improves final performance. This can be attributed to its update mechanism. To understand the impact of the momentum term on the outer optimizer, we conducted comparative analyses between Atom W plus SGD and Atom W plus Nesterov under both synchronous and asynchronous training settings. The results show that in asynchronous Local-SGD, Atom W plus SGD, which lacks a momentum term, leads to better final perplexity and learning efficiency than its synchronous counterpart. However, incorporating Nesterov momentum into the outer opt significantly boosts the performance of synchronous Local-SGD, outperforming the asynchronous version. It's noteworthy that asynchronous Atom W plus Nesterov remains the best performer across all tested combinations of inner and outer optimizers. This observation indicates that while momentum is beneficial in asynchronous Local-SGD for language modeling, its effect is more pronounced in synchronous settings. We further applied the asynchronous Local algorithm with homogeneous devices to minimize the stalled gradient problem in Local-SGD, which refers to the fact that we are using an outdated outer gradient to update the server model. The results reveal a notable finding. Even with homogeneity among workers, asynchronous Local significantly lags behind its synchronous counterpart. This suggests that the inherent staleness from sequentially applying simultaneous updates leads to considerable performance drops. To elucidate this effect, let's consider a scenario with 4 workers providing identical outer gradients. The standard Nesterov momentum update is outlined in an equation. In a sequential application of pseudo-gradients, we observe that sequential application results in a more rapidly decaying momentum term but amplifies the actual change in parameter. Consequently, a higher momentum maintains more recent momentum but may lead to greater changes in parameters, and vice versa. Importantly, this imbalance cannot be simply rectified by reducing the learning rate. Section Summary. In this section, the authors investigate the effect of different combinations of inner and outer optimizers on language modeling performance in asynchronous Local-SGD. They find that combining Atom W as the inner optimizer with Nesterov momentum as the outer optimizer yields the best results. Additionally, they observe that incorporating Nesterov momentum into the outer optimizer significantly improves the performance of synchronous Local-SGD, but its effect is less pronounced in asynchronous settings. Furthermore, they find that the sequential application of simultaneous updates in asynchronous training leads to considerable performance drops, even with homogeneous workers. Section: Baselines. We've looked at several established methods from the literature and tried to apply them to an asynchronous setting. These include 1. Fine-tuning a single worker with a larger batch size, which is similar to synchronous stochastic gradient descent, SGD. 2. DLoco, a synchronous Local-SGD method that combines AtomW with Nesterov. 3. The asynchronous version of DLoco. We also explored potential solutions from the asynchronous Local-SGD literature to address the challenges we observed. We considered the following methods. 1. An extension of asynchronous DLoco that reduces the weight of the pseudo-gradient based on how stale it is. 2. A version of asynchronous DLoco that discards updates if they are too stale. 3. A version of asynchronous DLoco that uses delay compensation to approximate true pseudo-gradients. This involves using a stale gradient and a first-order Taylor approximation to estimate the true gradient. In practice, we approximate the Hessian using a diagonalized gradient outer product. We apply this technique to pseudo-gradients instead of gradients. 4. A method that accumulates and averages all gradients in a first-in, first-out manner before applying Nesterov updates. This is a variation of the original Fed-Buff algorithm, using AtomW plus Nesterov. Our observations showed that reducing the weight of the pseudo-gradient based on staleness had limited benefits. Thresholding and delay compensation techniques didn't offer much improvement either. The method that accumulated and averaged all gradients showed promise in terms of convergence but was unstable early in training. Importantly, none of these methods performed as well as the synchronous DLoco method. To address these challenges, we developed two strategies. 1. Delayed Nesterov update. This strategy involves using the Nesterov update intermittently and aggregating pseudo-gradients in a buffer between updates. We update the model parameters using gradient descent, with a small fraction of the old momentum. We introduce a parameter to balance gradient and momentum-based descent. A value of 0 for this parameter indicates pure gradient descent between Nesterov updates, while a value of 1 evenly distributes the momentum term over the updates. 2. Dynamic local updates. This approach considers synchronous training as a solution, where pseudo-gradients from all workers are synchronized. However, the diversity in device capabilities often hinders simultaneous pseudo-gradient returns. A viable workaround involves customizing local training steps based on the processing speed of each device. This adjustment allows slower workers to execute fewer steps, aligning the completion times across different workers. Incorporating a grace period for model synchronization in this setup further reduces the impact of stale gradients, improving overall performance. Section Summary. In this section, the authors explore various synchronous baselines and their naive application to an asynchronous setting. They also investigate potential fixes from the asynchronous Local-SGD literature, but find that polynomial discounting, thresholding, and delay compensation techniques do not offer significant improvements. The async buffer method shows promise but does not match the performance of the synchronous DLoco baseline. To address these optimization challenges, the authors propose two strategies. The delayed Nesterov (DN) strategy, which intermittently uses the Nesterov update and aggregates pseudo-gradients in a buffer, and the dynamic local updates (DYLU) strategy, which customizes local training steps based on the processing speed of each device to align completion times. Section: A minimal toy example. We're going to simplify and explain a small example that we've created to help future researchers and to test new ideas quickly. This example is designed to mimic the challenges we've noticed when using asynchronous Local-SGD for optimization. The task is to classify data that is a mixture of Gaussian distributions. When we compare our example to previous ones, we see that it presents the same optimization challenges. We've conducted experiments to test the effectiveness of two methods we've proposed: delayed Nesterov (DN) and dynamic local updates (DYLU). We've also studied how these methods perform when we change the number of workers and the size of the models. When we compared asynchronous Local-SGD with DN and DYLU to other methods, such as single worker fine-tuning and DLOCO, we found that combining DN with DYLU significantly improved results. This combination was more effective and time-efficient than the other methods, even outperforming the synchronous DLOCO's performance over updates. We also looked at how DN plus DYLU and vanilla asynchronous DLOCO performed under different levels of worker-device heterogeneity. We found that DN plus DYLU consistently performed well across all levels of heterogeneity. Interestingly, even when the devices were all the same, vanilla asynchronous DLOCO struggled. This suggests that the problem may lie in the sequential application of pseudogradients, highlighting the importance of delayed momentum updates. We also tested DN plus DYLU with different numbers of workers and different model sizes. As the number of workers increased, the benefits of Local-SGD training decreased. However, DN plus DYLU performed similarly to synchronous DLOCO, showing its potential as an alternative in heterogeneous settings. When we applied DN plus DYLU to models of different sizes, both synchronous and asynchronous Local-SGD methods performed better than fine-tuning a single worker with an increased batch size. This advantage was more noticeable during the later stages of convergence. Our proposed DN plus DYLU method performed consistently well across various model sizes. We also tested the effect of applying a constant value, either 0 or 0.1, in async. DN plus DYLU with varying numbers of workers and model sizes. We found that there was no significant difference between the two values, indicating that adding slight momentum at intermediate steps doesn't help much. Therefore, we decided to use 0 as the default value in our algorithm, which corresponds to performing SGD updates between two consecutive Nesterov updates. Finally, we reviewed the literature on federated learning and Local-SGD style distributed optimization, focusing on their applications in asynchronous settings. Local-SGD is a specific distributed optimization technique designed to reduce communication frequency. It was later applied to the federated learning setting, leading to the development of the FED-AVG method, which aims to reduce communication overhead. However, as client-worker heterogeneity increases, the convergence rate often deteriorates. Methods like scaffold and MIME have been introduced to adapt these optimization methods for heterogeneous environments. Section Summary. In this section, the authors present a minimal toy example that replicates the observed optimization challenge in asynchronous Local-SGD. They conduct experiments to evaluate the efficacy of their proposed methods, delayed Nesterov, DN, and dynamic local updates, DYLU, and compare them against baselines. The results demonstrate that DN combined with DYLU significantly reduces perplexity and outperforms in terms of time efficiency, even under varying degrees of worker heterogeneity. Additionally, the authors apply DN plus DYLU to models of different sizes and observe consistent efficacy, highlighting the advantage of Local-SGD methods over fine-tuning a single worker with an increased batch size. Section: Asynchronous Training. We developed asynchronous training to address the straggler effect seen in synchronous distributed optimization. This effect slows down learning efficiency because it's dependent on the pace of the slowest worker. However, asynchronous optimization comes with its own challenges, such as the stalled gradient problem. This problem arises when an outdated gradient is used on a recently updated model. To tackle this, we use asynchronous SGD with delay compensation, which estimates the true gradient using the old one. We've also applied asynchronous methods in federated learning scenarios. Despite these challenges, asynchronous training has proven successful in language modeling, especially when using diverse devices worldwide. We've also used the concept of Local-SGD, or FED-AVG, in language modeling. For example, we've used cross-device federated learning to pre-train and fine-tune language models. More recently, Local has expanded the Local-SGD approach to include larger language models, specifically suggesting the use of atom W plus Nesterov momentum as the inner opt plus outer opt pairing. In asynchronous settings, the fed-buff algorithm stores pseudogradients from clients and only updates the server model after gathering enough pseudogradients. Timely FL aims to reduce asynchrony by allowing slower devices to train only parts of the model. However, our study has some limitations. Firstly, we've identified a significant optimization challenge related to momentum updates in the outer opt, but we're still not sure what's causing this issue. This presents an interesting opportunity for future research. Secondly, our observations suggest that the benefits of the Local-SGD method decrease as the number of workers increases. We're still trying to understand why this happens, but it's currently limiting the scalability of asynchronous Local-SGD. Lastly, while our proposed method dn plus dylu shows improved performance, it doesn't have formal theoretical convergence guarantees. This is something we need to investigate further.